This means this is the ball A epsilon, and the closed ball this is a sequentially compact set, closed and bounded set, sequentially compact. So our Psi is a C1 function. Of course, it's so if it's a sequentially compact set, the ball, the domain of definition of our Psi, this set is sequentially compact. Psi as a C1 function is continuous. Therefore, it has a minimum point in this closed ball, in this set. But when x is our this argument, this computation tell us that when x is a point in the boundary, in the sphere, on the boundary of this ball, the value of Psi x is strictly greater than the value at the center of the sphere. So the minimum point could not taken on the boundary. The minimum point is taken in an interior point here. So the conclusion is that there exists a point Psi in this ball, open ball. This point is not on the boundary, so that the value at this point is not greater than any other point. Okay, so as an integral minimum point, this is a local minimizer. This point C is a local minimizer of Psi. Actually, it is a global minimizer. But so the Psi is differentiable. Therefore, by the Fermat theorem, the gradient of Psi at 0 is 0. Okay. So we have this conclusion. Now we compute the gradient of Psi, of our function Psi. Psi x is fx minus y square, which can be considered as inner product. Y is given, the variable is x. So previously we have a proposition about computing the derivative of a function. The derivative of the inner product of two vector valued function. We know that Psi point Psi is this is 0. This is the gradient of Psi, the same. Then this is the fx minus y, fxc minus y transport f point Psi. Twice of this. Okay. Because the other term also f Psi minus y transport f point Psi. Therefore, this is 2 f Psi minus y transport f point Psi. Okay. The derivative of Psi at the point Psi is given by this formula. So at this point, at this minimum point, we have f Psi minus y transport f point Psi is 0. Or you can have f point Psi transport f Psi minus y is 0. But now this is invertible matrix. Actually, we don't need to transport. Sorry, we don't need this. Here is okay. Multiplying both sides by the inverse matrix of f prime c. Because the determinant is not zero, therefore the matrix is invertible. So we multiplied the inverse matrix from right. We obtained fc minus y is 0, or y is fc. Of course, fc is a point of the image. So we prove that is this argument is valid for every y in a half of mu neighborhood of B. Such a y is contained in the image of our map. So this B, the center of this ball B, is a integral point of the image. So the image is open set because every point B is an integral point. Okay, so this means that and B is an integral point. And proving our this important lemma. So we write the lemma we just prove here, and give you present to you an interesting application. The lemma is that G open F is C1, and for any x in G, the determinant is not zero. Then the image is open. Okay, this is the lemma we just proved. Now this lemma is very important. It has many applications. Of course, we prove it here as a proliferation of our proof of the inverse function theorem. But now we have another interesting application. When we study the Fermat lemma about the minimum point, that is, if a function is differentiable at a minimum point, then the gradient at that point is 0. Okay, remember this result. Then as application, we have such a example. F is Rn to Rn, say 1. For any x in Rn, the Jacobian determinant is not 0. And then we also assume that x goes to infinity, fx. Okay, then our result is that f is surjective. That is, the image is Rn itself. Okay, we have this result. Now we have proved this result using a method quite similar to our proof of this lemma, also by considering a function similar to this one. Okay, this is our previous proof of the conclusion in this example. Now, having proved this lemma, as application of the lemma, we can give a second proof of this important example. For G is Rn itself, applying the lemma, we see that it's open. Okay, compare the conditions, compare the assumptions. We see that the map, the map F satisfying all the assumptions for the lemma. The assumption is C1 and the Jacobian determinant is nowhere 0. This is our assumption for our map. So applying the lemma, we see that the image is an open subset of Rn. Okay, so this is the first observation. Second, by a problem of our quiz, because the limit is infinity, because of this condition, we know that the image, no, not G, our G is Rn in fact. So this is Frn. Okay, so now from the problem in our second quiz, we know that because the limit is infinity, we know that this is a closed subset of Rn. Okay, now the image of this map is closed and opened, and of course it is not empty. Okay, so Frn closed, opened, and not empty. It must be the whole Rn. Okay, this is a result we proved previously. We have a section when we study continuous function. We have a section about distance from a point to a subset. Then, as application of the result in that section, we prove that there is the only non-empty, open, and closed subset of Rn is Rn itself. I repeat it again. The only closed and opened subset, if not empty, it must be Rn itself. So this subset, this is the subset. It is closed and opened and not empty. Therefore, according to the result I just recorded, it must be Rn. Okay, so this is the interesting application of the open mapping lemma. We just proved. Okay.